corresponded to just intonation. That's what they mainly refer to. But continuing, is it enough?
I guess it's yeah.
Continuing with my lectures on the literature, I found some sentences that somehow confused me a little bit. So, for example, here Shankar says that they do not use strict frequency values of tuning. So, and he advocates, she advocates for an infinite space of microtonal values. So this, for me as a Westerner, was quite strange. And finally, she says that for that a framework of 22 shrutis means notes in the Western sense, was used. In fact, these 22 nodes are already acknowledged in the Wikipedia. If you continue reading the article on the Wikipedia about just intonation, you have the 22 shrutis or nodes used. But then, if you go again to the textbooks, you find more confusing things. For example, Sambamurti acknowledges other different number of notes, not only 22, but 24, 27, 32, 48, 53, and 96. So, being a Western musician, using 96 notes for me was really completely ununderstandable, no? So I had several questions in my mind that I thought we could solve in a quantitative and objective way. So the first question it came to my mind was, is just intonation really used in Indian classical music? The second question was, is it used today, or it's just some feature from the past? A third question was, has contemporary practice been influenced from Western music? So is it nowadays this schema of tuning used in music? Another question was, is it true that Indian classical musicians use more than 12 notes? And more important, and which is the rationale for doing this article, is can we provide some quantitative and empirical answers to these questions, not only looking at textbooks and looking at musicology, but looking at the signal, at what is actually played. So if you search the literature on music processing or music signal processing about these concepts, you find that actually the tuning in Indian classical music is a matter of debate. First of all, the tuning is debated, so there are some authors who claim it's equal temperament, there are some authors who claim just intonation is still used, but also the theory of these 22 notes is debated. Some authors do not find evidence in the signals of the performances about the existence of these 22 notes. Some authors yes, some authors found evidence for more notes. So there is different opinions. What seems more or less clear is these three facts, no? That they find a high variability in the intonation of notes, so the idea of a continuum of tunings would more or less could be true. The second thing is that there are two tuning systems that are more or less acknowledged by the researchers, which is equal temperament and just intonation. And there are two blocks of evidence, one for 22 notes and the other for 12 notes. But in general, these papers provide many contradictions. They use few audio data. Some music they use is not realistic, meaning that maybe they record some musician with a piano, which is an already well equal-tempered instrument. The methodologies sometimes are not clear. So we tried to devise a simple and methodology to be applied to real audio signals from Indian classical music and try to guess which are the answers to those questions. So first of all, what we decided to study is the singing voice. Why? Because first, it is not constrained in its pitch control. It doesn't have specific tunings, so tune it to what you feel, let's say. Then second, because the singing voice in Indian music is the main reference to be followed by other instruments, so it's I would say the key part of an Indian music performance. And third, because it has many solo or predominant sections where the voice is omnipresent, I would say. It's really loud compared to the rest, so this means that it's easy to analyze. You don't really need to do a source separation or anything like that, so the voice is practically alone, so you can analyze it. And in analyzing the voice, we wanted to focus on stable tuning regions. So assuming that no intentional tuning can be done in a very short or tuning unstable utterances. So just focusing on places where the tuning could assume more or less to be stable. I will explain later what it practically means, this sentence. The music we used, so first we used a synthetic data set just to cross-check our methods. So basically we synthesized MIDI scores, but using different tunings. This can be easily done with the software, Pianotech. Then we analyzed real recordings of Indian music, both Carnatic, music from South India, and Hindustani, music from North India. Well, having male and female singers, different epochs of the recordings. And we selected excerpts where the voice, as said, was very loud when compared to the rest of the instruments. Finally, we used some comparison data set, which are Western pieces, but which are solo tracks like fretted electric bass and a cappella singing voice, solo a cappella singing voices. So in our methodology, the first part is to estimate the fundamental frequency of this singing voice. For that, we use the well-known yin algorithm by the Chevenier and Kawahara, and we adjust its parameters manually. The details are in the paper. I won't go into these details. But this algorithm provides two things. One is a pitch contour of over all analysis frames. I put it here in sense because we reduce the resolution, but in principle it provides the contour in hertz, so you could easily extrapolate this resolution. And also it provides a confidence value for each frame, meaning that if the software is very confident on that pitch or not. Then what we did was this fact of considering only stable regions of pitch contour motivated because complete transcription is not needed. We don't want to transcribe every possible thing that has been recorded, only things which we are really sure that are there, and only parts where the tuning can assume to be more or less constant. This reminds of other concepts applied to this kind of studies, for example, the idea of conservative transcription or the idea of a steady state detection. So this is not new, this is in the literature. Some guys have used these techniques. And we decided to keep the scent and the confidence values. So to define this stable term here, what we did was to keep the scent and the confidence values of windows centered at the region of 400 milliseconds, considering stable a deviation less than 20 cents in the pitch contour on this nearly half a second window. So we only kept these values. Okay. Then what we did was to compute an interval histogram. For that, we first compute a weighted histogram. This is not the interval histogram, but it's a sub-step previous to the interval histogram. So this histogram has a resolution of cents. It ranges from the minimum to the maximum possible pitch value. This is already specified in the yin algorithm. In the yin algorithm, you need to specify a minimum and a maximum pitch value. We don't care about memory requirements. We specified a wide range of pitches. And then we used the confidence values as weights for this histogram. So in the way that if yin is very confident about that particular pitch, then it gives +1 in the histogram. If it's not so confident, it's plus something less than 1. Then to facilitate peak selection from this histogram, we do a mean smoothing. So we take the mean over a 12-cent window across the histogram, and we normalize this histogram between 0 and 1. Notice that no octave equivalence is applied yet. So this will allow us to distinguish between 12 intervals higher than 600 cents. Then we compute the interval histogram. For this interval histogram, we select prominent peaks from this weighted histogram before, and then compute all possible differences between these peaks of the histogram. So this means that we are actually considering intervals. And finally, now we apply an octave equivalence and collapse all the intervals to one octave. This means that we have a histogram between 0 and, well, 1 and 1,200 cents, or 0 and 11.99 cents. Finally, to facilitate visual inspection, we apply a mean smoothing technique again, but now the window is smaller so that more detail is preserved. Finally, the histograms are normalized between 0 and 1, also to facilitate visual inspection. So the results, but before showing the results, I would like to explain a little bit what's this picture here. So this is where the histogram will be placed. Here we have the cent values, and here we will have the relative frequency or the relative energy of each cent value. And then these lines, the straight lines, are the places where equal tempered intervals would be placed. You see a straight line at 100, 200, 300, 400, 500. Then the dash dotted lines, for example, this one, are places where just intonation interval can be placed. So remember that these are intervals, are not frequency relations. Okay, so there are more than 12. And finally, the dotted line is where idiosyncratic intervals for the 22 notes could be placed. Some of the intervals of the 22 notes overlap with the just intonation ones because they share several frequency relationships. But there are some idiosyncratic places, for example, here, here, and here, where only an interval corresponding to a 22 note scheme could be placed. Then, for synthetic data, okay, nothing special. We see that if we synthesize with equal temperament, all the peaks of the histogram are in equal tempered positions. This confirms that our method more or less works. The same with just intonation. So we see that depends on the notes you synthesize, of course, no. But in general, you have peaks on the just intonation places for these intervals, no. For example, here it's very clear. So then, jumping to Carnatic music, what can we say about that? In general, peaks are closer to just intonation locations. For example, if we see here, we see some locations to just intonation, or even here, it's closer to the just here there is a small dash dotted line next to the straight line, or there. So in general, we see that the intervals correspond more to just intonation. If we do some analysis of correlations, we see that the correlation with Carnatic music with the histogram obtained with just intonation is higher than the correlation obtained when comparing Carnatic music and equal temperament. And this difference is statistically significant with a quite reasonable p-value. So in principle, it favors the theory that Carnatic music uses just intonation scheme. The peaks we found in detail by zooming at each region are listed here, the most prominent ones, and then we show the nearest just intonation interval and the nearest equal temperament interval. You see that the differences are consistently smaller than with equal temperament. Then, for the Hindustani music, the North Indian music, we see that the histograms are a little bit different. So, few values are distributed near just intonation locations. For example, maybe just 92 cents is closer to a just intonation location. 223, this point around here, maybe is a peak corresponding to just intonation. But, however, the majority of prominent peaks lie near theoretical equal tempered intervals. So you can look at 300 cents, for example. You can look at 400 cents. You can look at 800 cents. So, in general, we find that Hindustani music is maybe a hybrid, but tending towards equal temperament. If we study the correlations, we see that the correlation versus equal temperament is higher than the correlation versus just intonation. also statistically significant at a very decent p-value. So in general, we see that there is a clear tendency towards equal temperament. Which is the hypothesis? Why does it happen? No, in principle, in the books we read that Indian music uses just intonation, but in the case of Hindustani music, we see that it's not really the case. Our hypothesis is that is because the introduction of the hand-pumped harmonium. So the hand-pumped harmonium is this instrument here. It is mostly an equal temperament instrument, and it was introduced in Hindustani music in the late 19th century, and it has been used extensively to accompany the singer soloist. So we hypothesize that the really extensive usage of this instrument has influenced the way singers sing and singers tune their melodies. So finally, comparing both directly, we can see some facts. So first, that Carnatic music presents less peaky histograms, so these histograms are flatter. Remember that we normalize between 0 and 1. So these histograms are really flatter, so this means that in Carnatic music there is less preference for specific interval locations, while in Hindustani music these intervals are more clearly defined. So this supports the idea of Swarastani or Swarastana or note regions in Carnatic music, but not really in Hindustani music. This is the case for Hindustani music. Then about the use of 22 notes or 22 shrutis, it's very controversial. So in Hindustani music, there are no peaks at all at these idiosyncratic locations for the 22 shrutis. So here, for example. In the case of Carnatic recordings, it's not so clear, but we would say that there is not much support. For example, if we look here, we find no energy. If we look here, we find no energy. If we look here, no energies are found. Although in some places, so maybe here, there is some energy, or here at these idiosyncratic locations. Finally, to compare with Western practice, so we used those tracks from Electric Fretted Bass and from vocal Motown a cappella recordings, if you remember. So this is the histogram for the electric bass. Again, no special things, so just to cross-check the algorithm. So prominent peaks are close to equal temperament locations. If the bass is correctly, if the frets of the bass are correctly distributed, this is what should happen, no? The correlations, of course, are really clear. So the correlation with equal temperament is higher than the correlation with just intonation, also statistically significant. In the case of vocal Motown tracks, the thing is a little bit trickier, because prominent peaks, of course, are near equal temperate locations, but we also see some other peaks closer to just intonation. For example, here in 92 cents, or in 112, etc. The histogram correlations are also unclear, so they are really, really the same, or more or less the same, and the difference is really small, and it becomes being not statistically significant. So this issue is left for further work, for further work to study why vocal Western tracks are not really completely equal tempered. So basically, the conclusions of the article are many. So first, we show that a simplistic approach using standard techniques allows us to assess the tuning of some music in an empiric and quantitative manner. Second, we provide evidence that Carnatic music does not make use of an equal temper tuning, so these hypotheses can be discarded according to our data. In fact, it presents a strong correlation with just intonation. And another conclusion is that Carnatic music is less confined to strict intervals. Conversely, in Hindustani music seems to be explained by a mixture of equal temperament and just intonation tuning. And it shows clearly a preference for stricter, more precise intervals. Finally, we cannot completely rule out the theory of 22 shrutis, but we have to say that in the view of our results, no really strong evidence has been found for this theory of 22 notes. So, yeah, that's it. Yes.
I wonder if you got some comments from musicians on these results. Like would a master from Carnatic music, a master from Hindustani music, would they oppose the outcomes, or would they accept?
I've personally have had no contact with Indian musicians, but I know Gopal and Xavier have.
I have like personally met some musicians. Rather, we did not say these results, and I know that they will be very curious and things. But I just asked them like, so if there are these 22 Sufis, then please can you demonstrate it so that we can learn. But nobody is really ready to demonstrate them. They only said we can only do that when we play a raga and it's like we use it on the stage. It comes while playing. I mean, they are not really demonstrating anything. So.
And well, but you couldn't get a comment of them looking at those figures.
Okay. So by then, when I met the musicians, we did not have these results, but we have another person like called Krishnamurti. He has worked on these things, and he claimed very bold statement. He says like 22 Srutis does not exist. They are only a perceptual phenomena, something called gamka, microtonal inflections. So, but he did not verify that with any behavioral or quantitative analysis. So I explained his theory to him, and the musicians are like very, they completely rule out such statements. So they are not in a position to agree anything that goes against 22 Srutis. They are very much opinion that they are still used.
In the process, you analyze everything by taking the stable regions.
Sorry?
Stable regions on the page cognitive.
Yeah.
Yeah. So do you think like removing the non-stable regions, which is like one of the characteristic like signature of Carnatic music, is like not using a significant data which might reflect?
Well, if you think that you are able to tune to something, to some schema in less than 400 milliseconds without 20-cent variance, which is the conditions we apply here for stability, I don't think that's tuning. I don't think that a human is able to tune at that detail. Maybe I'm wrong. But another reason for using these stable regions is to make the histograms more peaky. Maybe. So you are somehow pruning the deviations from the peaks of the histogram.
Conceptually, that you don't like say like this node should be this, the tuning should be like this. They define a region like Swarasthana. It can be anywhere in that region. So
yeah, this is not ruled out in the. So if it's stable, whatever the place it is stable, it's kept. So if it's stable within that region, we keep the data. If it's not stable, not. And we allow for a vibrato of 20 cents, which is quite high, I would say.
I think like with the data we have taken, it is not possible to either confirm or rule out 22 Srutis. We need more data from the data from the mix of sessions, and I don't know how feasible it is to collect features from those regions. And when I like when we have another travel recognition program, so I expected like building more having more fine pins will result in like drastically improved radar recognition programs. So, but it did not help that much. The pitch value by itself cannot help, but what Krishnamurti he has claimed atomic value which has both the frequency and time. So it is a curve. So maybe matching those curves and saying like so this Gamaka touches these. So having such kind of like data points in all the like throughout the pitch contour can help us to see what are all the pitch values that which are claimed to be are present in this pitch contour.
That's one of the future works discussed in the paper already.
What about tuning of the instruments? I mean, I was can each of them tune to other notes on it? And do you have any fixed frequency tuned instrument? Or is it all fretless?
For 22 rupees?
Well, to whatever. I mean, for example, if I would have an instrument with 5 strings, each tone is tuned to another frequency, then that is again another evident value information.
Yeah, the problem is that nowadays they can make instruments, string instruments, for example, tuned to whatever.
Yes.
If you Google a little bit, you find some luthiers making instruments with 22 shrutis or 96 shrutis.
Yes, I see.
So this is a little
But,
bit.
well, I would, let's say, if I want to use such kind of data, I would use it from the masters. I mean, maybe the masters themselves have some fixed frequency instrument. Do they have it or not?
No.
Usually it is fretless in case of Carnatic.
Okay.
It's
No fretted instrument.
There is. Veena is a fretted
But-
instrument.
yeah.
But I mean, the frequency slots are not fixed. I mean, each fret
Okay, you
does
can move it.
Yes, I mean, for some Veenas it is movable, but even those with fixed frets, I mean, they define their own frequency by tuning the strings and like 22 shrutis, they are not indicated on that Veena.
Okay, well, I'm not only asking in the context of 22 shrutis
Okay.
or so. I'm just asking if there are fixed frequencies, whatever shruti or not.
No, in Carnatic music, no. But there
They
is some
tune everything. For example, if you have multiple string instruments, you tune everything to one single note or
No, that's the thing. So there is the tonic and the
Okay.
fifth.
Okay.
And even the fifth is a region like I mean, it depends on the tonic. So those two strings, like suppose the violin, there are 4 strings, and like they are tuned to sa, fa, sa, fa. Sa
Okay.
is the tonic, and p, pa is the fifth.
You only have a 50 interval and a 40 interval.
Sorry.
Yeah.
I'm interested in the intervals between these frequencies of
Yes.
these open strings.
Except for this sa and pa, every other frequency is defined as a region. So in one raga, you
But
sing.
how can you tune a string to a region? You tune it
No,
to an exact.
it is tuned to the tonic and the next string to the fifth.
Okay,
And you
this is
can
what
move
I'm
your fingers for other frequencies so that they are movable. I mean,
That's okay. I mean, but well, the open strings give you an evidence
yes.
about an interval. Of course, you can move everywhere, but you would hear it sound itself, that open string, in the music at some point.
Yes.
So those points should be fixed. Those points should not be interval.
They are fixed. Indeed, like there is a classification scheme for raga in Carnatic music, which uses these 2 fixed points to organize all the ragas into 72 grand scales. They are called Malagartha. So
So you only have this fixed fifth
yes,
interval.
yes,
This was
And
what I'm
the
asking.
fifth
yes.
and the fifth is the same with equal temperament and
Very
just
close,
intonation.
yes. Very
And
close.
other values are like,
702 cents.
Yeah.
other values are more. They are more dependent on the raga and stuff.
You posed the question about historical development in this,
Yeah.
in this behavior. Did you find any differences between old recordings, new recordings?
The thing is that the harmonium, this instrument, was introduced in the 19th century.
Yeah.
We only have recordings of the 20th century.
Yeah, but for example, for Carnatic music or whatever, in whatever context, could you see some significant differences, let's say, between recordings from the beginning of the last century and the
No, we didn't look at it. It certainly would be a nice paper to look at that, no, and to have the exact date of the recording of that performance, no, which is a thing we didn't have for all the pieces also.
Yeah, but at least you would have possibility to separate it into very old and very recent recordings.
Yeah, but with the recording you don't have the year. We have some of them in our collection.
Yeah, but
We should be strong in musical things and in order to know the person's time and who is the person singing that. And the metadata is very bad.
recordings, which the ones probably in the library?
No, these were from my previous like master's program, Carnatic ones, and Hindustani ones are from master thesis of Marius.
And like all of these are commercial recordings.
Yes.
Okay. And like so you know, Bashkostik was saying like maybe checking with masters might be a nice thing. So like maybe making like kind of you know isolated recordings or like using them might actually help in you know understanding like maybe you know as an additional data set. Not
Yeah. But maybe more important is what Gopal was pointing out before. So studying just single ragas, because each raga maybe could thought of using its own tuning. So there are many possibilities to be checked here. No, either if a performer uses a certain tuning, or if a certain tuning is used for a certain raga, or well, many combinations here. The explosion is of combinations is really.
lots of stuff to do.
Okay, so I guess I have to switch to the next one, or the next one is not is not really about.
45 minutes.
The next one is not really about Indian music or Turkish music or whatever, but are more general concepts used in music annotation or in category-based retrieval, which basically consists on retrieving music based on annotations, categories, etc. So in category-based retrieval, there is a goal, which is to find music recordings in a collection that share some characteristic or trait. No? In general, we humans group objects into traits or categories, understanding a category as any word or concept that can be used to describe a set of recordings, no, that share that property. Synonyms for category you could maybe think about are class, type, kind, etc. of recording music, etc. So categories are one of the most basic ways of representing and structuring human knowledge, and they usually encapsulate characteristic intrinsic features of a group of items that all of them share. An interesting thing is that prototypes can be built, and then potential category members can be compared to these prototypes. This is a way of deciding if a new member enters into the category or not. And just notice that categories can overlap, for example, or can be organized internally somehow. I am giving some words about this later. So the idea of the task is simple. So you have an audio. Here, you analyze this audio, you extract some features automatically with the help of a computer. And with these features, the computer says that that audio is, for example, happy. Happy is an example of a category we could use to distinguish different audio items, no, in terms of moods. Then what you do is to query with this category a database and to retrieve a list of songs that share this category with the query. No? This is the general schema. Notice that instead of analyzing an audio, you could directly specify, I want to retrieve happy songs. No? And then the approach would be more or less the same. So some examples of category-based. So for example, you could, let's see if the audio works. You have this query, which is a bossa nova. And you would like to retrieve items like this. Also a bossa nova. But you do not want to retrieve items like this, which is a typical popular rock song. No, the same with many other categories you could think about. For example, sad. If you want to retrieve sad music, this would be the query. This could be considered as sad, and you would like answers like this. And you would not like answers like this, for example. And the same with many more categories you could think about. For example, you could query for specific instruments. You would like to retrieve songs with extremely distorted electric guitars, or songs played by a string quartet, or G minor pieces, or songs with lots of loudness changes, or types of recordings. For example, you would like to retrieve live recordings, etc. So we see that for this task, for category-based retrieval, the main objective is to label or annotate music documents. And ideally, apart from annotating them as being, for example, happy, we should annotate them with some confidence of that label and with some probability of that label. Documents are not 100% happy or 0% happy. Maybe they are 90% happy or 50% happy. And a confidence of this, as I said. Annotating music documents implies a taxonomy. A taxonomy can be gathered from different sources. For example, you could base this taxonomy on the opinion of experts, some musicologists that decide which are the important terms to be used to annotate music. Or either, as we have seen in Frédéric's presentation, you could gather this taxonomy from the wisdom of the crowd. So it will be a folksonomy, from what users say about a given song. Or the one I like best is the personomy, because it's me saying what's that. No, it's not somebody else saying that. So I understand. I agree with myself always. And yeah, remember that these taxonomies can be organized. These categories can overlap. Different relation types can be established between these categories, some hierarchical relationships, some categories relating to another one, etc. Which are the main global approaches to infer these categories? So there are two big branches. One is inferring them unsupervisedly. Here, there are no categories in the beginning, so it is supposed that categories emerge from data using a predefined similarity measure. And for this type of ways of inferring categories, we use clustering algorithms like k-means, self-organizing maps, etc. And the other variant, which will be the focus of the talk, is to using supervised learning algorithms. In this case, you specifically use a taxonomy, so you define a taxonomy before the experiment or before the task, let's say, and you try to map features, automatically extracted features from audio, to this taxonomy. And for this, you use typical supervised learning algorithms like k-means, neighbors, neural networks, supervector machines, etc.
Here, when you talk about category-based retrieval, we're not talking about genres, instruments, like genres being a category, specific instances of each category.
Yeah. And the categories, as I said, can be defined either by you, either by us, either by an expert, either by a community in the internet, etc. So, which is the motivation for using category-based retrieval? So, the main motivation is for searching and organizing music collections. If you can organize them according to some category that makes sense to the users, that's of course an added value. Also, for fun, leisure, to retrieve things that you like. And an important application here is playlist generation, music recommendation, and music similarity based on these categories. As Tversky showed a long time ago, the intersection in categories is one of the main features of similarity, in general, psychologically speaking, in general, I mean. So, which is the typical approach for automatic annotation? So first you have some labeled audio, some ground truth that you labeled according to a taxonomy. What you do is to extract some features from this audio. We are talking always about content-based approaches, so only using the audio content, not tags like the talk before. Okay. Then once you have these features, you do some data processing, you transform these features somehow, you select them, you reduce the dimensionality, you do several data processing techniques, and then you train some classifier, some supervised learning algorithm, and validate it, assess its accuracy. Finally, when you don't have, when the audio is not labeled, it follows the same process. You extract some features, you process the data, and just classify. You don't train anything here. You just apply what you have learned with the labeled audio. It's a classification stage, and this classification algorithm can provide you the annotation to the category name, but also the probability of this category and the confidence it has about this decision that the classifier has made. Just let's give some words about feature extraction. So the important thing about feature extraction is that features depend on the task. You cannot, well, it's a valid approach, I would say, to launch a pool of features, an immense pool of features, and then let the supervised algorithms select which ones are good for your class. But maybe if you think of this example, we will see that this makes things more difficult than they actually are. For example, if we want to infer the key of a piece, talking in Western terms, we would not use MFCCs because we know that these features do not provide any information about the key. No, it's mostly describing timbre or the spectrum shape. So if we include MFCCs in the task, it complicates things because then the classifier needs to realize that these features are not useful for the task, etc., which is a thing usually it does, but sometimes it can complicate things. So some knowledge needs to be fed into the task, selecting a priori the features you think are important for that task. A list of basic features is here, so you can use any feature depending on the task, either temporal, spectral, tonal, or rhythmic features. There are tons of papers describing different features. You are free to use the one you prefer for the task. And the important thing is that these features are extracted on a frame-by-frame basis. This means that we cut the audio into short snippets, and then these snippets are usually aggregated into a one feature vector to represent the global characteristics of the excerpt you are analyzing, of the part of the audio you want to consider. Usually the whole song, but sometimes just a part of it if you want. Ways to aggregate these features, well, typical ways are component-wise means, component-wise variances, covariances, higher order statistical moments, derivatives, etc. You can think of your own summarization if you want. But what happens that you usually extract many features and you need to do some processing on these features and you need to select which ones are useful. In processing these features, some processes that are usual, for example, is to rescale each feature so that all of them have the same influence in principle. So some classifiers do not really rescale features, so it is recommended that you do it before you apply the classification. No, you can normalize, you can standardize, you can even Gaussianize. If the distribution of your data is not really standard, you can apply some algorithm to make the distribution Gaussian. Then in this data processing, one objective is also to detect highly correlated features, and you may want to remove highly correlated features since they give exactly the same information. Sometimes you don't want to remove these correlations because maybe a specific classifier can exploit them, but it's usually not the case. You want to remove uninformative features. Basically, if a feature is randomly according to your taxonomy or to your concrete concept that you want to annotate, and you just want to discard this feature. One important thing is that you want to reduce the dimensionality. Usually supervised learning algorithms do not work well with high dimensionalities, so it's always advisable to try to reduce the dimensionality of the features, and they do not generalize well if they are using a higher dimensionality in the features. And most important in data processing, in processing your features, is to learn about the features and the task. Are your features good for this task or not? Which are the ones that a priori look more discriminative, etc. A typical feature transformation algorithm is principal component analysis. Principal component analysis is a linear transform. So let's say you have features x1 and x2 here, and it eliminates redundancy by correlating the two variables, creating two new axes. So it's a basis transform, and it also can be used to reduce the number of features. So it does several things at the same time. No, eliminates redundancy, that correlates variables, and can be used to reduce the number of features because the access, the higher the number of the access, the order in which is ordered according to the eigenvalues of the principal component analysis provides less variance explanation, so you can start removing some basis of this transformation. However, it has some drawbacks. One is that it assumes some homogeneity of your distributions. If your distributions are a little bit strange, maybe the principal component analysis does not capture the directions which contain most of the variance. And another drawback is that you lose the information of which specific feature is relevant. So PC1 here is a combination of x1 and x2. If you have multiple features, then PC1 is a linear combination of lots of features, and unless one has a high weight for this combination, you lose the meaning of this variable, the conceptual meaning. Then for selecting features, a typical approach is Fisher's ratio. So Fisher's ratio is based on the ratio between inter and intra-class scatter. And for example, in this case, it measures discriminative power of feature J between classes I and I prime. No, if the means, considering feature J, if the means of the two classes are really close, this ratio is close to 0, for example. So this means that they are not well separated. Therefore, this ratio gives you a measure of how well separated these two classes are. But then it has a drawback, which is that there is no standard way of performing this feature selection iteratively. So this is done for every feature. Then several strategies can be devised. For example, sequential backward selection. So you start with all features, you remove one, you calculate these Fisher ratios, then keep the combination that best performs on your data and repeat it iteratively. Or you could do the other way. So you start with just one feature, testing all possible discriminative combinations. The two that are most discriminative are aggregated into one, then testing again the combinations. So as I say, there is no standard way of performing this selection. In fact, there are many other feature selection algorithms that you could consider. So correlation-based feature selection algorithms, gain ratio, even combining these algorithms or selecting features according to your classifier, using your classifier to actually select the features by some iterative procedure like the one used with Fisher's ratio. So assuming that you have selected your set of features, now there comes the classification stage. And you could use several classifiers. A typical one is a probabilistic classifier. This operates by using the bias rule. And since this is more or less constant for the whole task, you focus on this probability, which is here, and it's where you apply the conditional independence condition, where you assume that each feature is independent given the class. This yields the naive Bayesian classifier, for example. How to set this probability? Well, this is where maybe Gaussian mixtures enter. So you say that the probability of a feature given the class corresponds to a Gaussian distribution. And with Gaussians, you expect to model nearly any distribution. So with a sum of different Gaussians, with a mixture of different Gaussians, if this number of Gaussians goes to infinity, in principle, you can model any distribution. Of course, computational costs are really prohibitive if the number of Gaussians is really high. Another classifier which is not so much different from Gaussian mixture models is neural networks. In neural networks, you have an input layer, which is your features, and an output layer, which is the probability of a given category, for example. And then you have several intermediate hidden layers where you combine inputs to deliver outputs. And the goal in training the network is training the weights and training the way to combine these inputs, usually in a nonlinear way using a sigmoid and with different weights for each sigmoid. A simple classifier approach, for example, is the k-nearest neighbors. In the k-nearest neighbors algorithm, once you have a new sample, would be this ring sample, you select a distance threshold, and then you look to the majority voting of these neighbors. No, in this case there are 2 red triangles and just 1 blue square, so you would say that the green sample is actually a triangle because more triangles are close to it. Another common classifier is trees. In trees, you basically threshold your features according to your training data. And for example, if some feature is below a certain threshold, you go to another branch. If it's equal to something, you go to another branch. If it's between this value and this value, you go to another branch. You keep branching your features, and depending on the branch level, you select one feature or another. And in the end, you expect to have groups of features, homogeneous groups of instances here, depending on the different thresholds you have applied in the tree. This technique has the advantage that you actually see which feature is deciding what. So if you here only have, let's say, heavy metal songs, then this means that feature A is really discriminative between heavy metal and the rest of the concepts or of the categories, no? So this is an advantage of trees. Unfortunately, they usually do not perform really. The accuracy of these classifiers is not the highest among classifiers, but it gives you a good impression of your features and which are useful and which are not. Finally, a really common classifier are supervector machines. The trick of supervector machines is to map the input space defined by the features into a different feature space, usually with higher dimensions, but where the partition can be made with hyperplanes. So the trick is not in partitioning because you just select hyperplanes, but the trick is in the mapping of this kernel from the input feature space to another feature space. Then, as I say, the division between the 2 classes or the 2 concepts is done by hyperplanes, and the interesting thing about this technique is that hyperplanes are only defined by a few support vectors. So you don't really need a lot of storage to store these models, but just the support vectors. And then in the splitting, since it is a hyperplane, it can be a really fast technique. Many other classifiers are here, so combinations of different trees to try to improve accuracy, logistic regressions, or you could use ensembles of classifiers, for example, launching different classifiers and then devising some schema to try to decide on which category corresponds to that audio. Fortunately, we don't have to implement all these. We have lots of tools that already implement these approaches. No? 2 of the most well-known ones are Weka and RapidMiner. So they basically are big software packages that allow you to combine classifiers, to use them with the same data set, to analyze, to visualize features. So they are really nice packages that allow this annotation. They can also be used with source code to really implement your data. Other packages for MATLAB, for Python, or for R are available, equivalent packages. Not with the nice GUI interface, for example, that Weka has, but with some functionality with the scriptings. Finally, to conclude, I would like just to highlight some issues with classifiers, really basic issues, but that sometimes we forget, and if we forget them, we are not doing things properly. So, for example, the first issue when doing this kind of annotations based on supervised learning, the first issue is to perform a visual inspection of your features. Sometimes you just use the tools and do not check visually the features. By checking visually the features, you can know many things apart if your algorithm outputs some NaN values. Apart from this, you know the distribution of each feature. You can see, well, by seeing this distribution, maybe with the tree, this would work because if it puts a threshold here and a threshold here, then we can separate the distributions. So you already can have an idea of which classifier to use by just looking at your data. Or for example, here, if I look at this feature, these are 2 features only. A Gaussian mixture model here would work very good. No, just 1 Gaussian for the green points, 2 Gaussians for the red points, and maybe 3 for the blue points. But that's everything you need to model this kind of data distribution. No? Or also, visual inspection allows you to assess the redundancy of 2 features. If you plot two features and see something like this, this means that they are really correlated, so maybe you are interested in discarding one. Or maybe you can infer that they mean the same. Sometimes features have different names. One is named blah blah blah, and the other is named X. So you can infer that they are both describing the same, even if they are not obtained in the same way. Another issue is, it's really obvious, but sometimes it's forgotten. So it's, do not classify M items with D features when D is larger or comparable to M. And as a rule of thumb, this is a personal rule of thumb, but I always try that the number of instances used in my classification experiments is more than 20 times higher than the dimensionality of my features. Why do you need to care about that? So let's suppose you have two instances and two features. So the dimensionality and the number of instances is comparable. How would you split this set? Placing a random line, no? Your classifier is not general. It doesn't generalize for other instances that can apply anywhere. Your classification is surely wrong. So there are many, but this is easy to see in 2 dimensions, but sometimes you have 1,000 features and 1,000 instances, and you do this the same. This in higher dimensions is even worse, because every time you add a dimension, the possibilities to split randomly the space grows exponentially. Another thing, when you compare different classifiers or different approaches, be careful in the number of features they use. No? It could happen that one classifier is just exploiting 2 features while the other is exploiting 3. So it's obvious that, it's intuitive that this classifier in the same conditions would perform the same maybe than the other one, but since they are exploiting a different number of features, their accuracy is not comparable. As I say, this is very obvious, but sometimes people forget these things. The next thing is use balanced data sets. If possible, balance your data set. Typical way to balance your data set is by random sampling your data set and running several experiments with the same amounts of instances per class. So although even the reality could be that maybe you have a class with 90 features and 90 instances, and the other you only have very few instances, well, if you really need a classifier for that, train with 10 and 10 and do it several times for the rest. Then a problem with classifiers is always overfitting. To illustrate what overfitting is, I have this small animation. So here in principle, if you have this data, this diagonal line would be the ideal solution of your problem. However, if you have the same problem with a smaller data set, let's say this, we have removed some points here, and you learn some solution here, maybe you could think of learning this solution, which is a complicated solution. It's not a straight line, it has many steps, and it's really a complex solution. Then when you classify the new data, you would produce 3 errors. Otherwise, using a simple line, a less complex classification, you would just achieve 1 error when classifying new samples. No? So this is a little bit the problem you have in overfitting, using complicated models to explain few data. So how to reduce this problem of overfitting? Well, basically, try to use algorithms that intrinsically generalize well. Pursue simple things, simple classifiers usually generalize well. So the simple things are the ones which are more generalizable. As you introduce parameters in some algorithm, this algorithm becomes less and less generalizable. If these parameters really matter, of course. If they don't matter, it remains generalizable. And in the evaluation, use suitable measures for evaluating it, and more importantly, evaluate the performance of the model with data you did not use, which is we have done in the previous example. No, we kept aside some part of the data, and then we evaluated with that data, and we saw that we got 3 errors with the complicated model. No? These strategies of leaving out some data, there can be many strategies. The typical one is the holdout cross-validation. For example, you split your data into some train and some testing. Otherwise, you can apply a cross-fault validation. So you split here in 6 your data into 6 different blocks, and then you use 1 as a test and the remaining 5 as train. and you do it several times. The important thing of all these splitting methods or validations is to ensure a number of repetitions that is enough to get statistical significance there. Because it could be that this partitioning is really trivial to classify, but once you partition many times, then you are sure that you are generalizing your classifier. Next thing, check the default parameters of your classifier. These packages like Weka, for example, the classifiers come with default parameters. And usually people run the default parameters and report the accuracy. Okay, be careful because, for example, I remember running a general classification task with some trees, and I got a 95% of accuracy. And we were testing a new set of features, and I was really happy. Wow, 95% of accuracy, and people with this data set only got 80% of accuracy. But then when I realized I was using the tree, and I realized that the number of instances in the final tree branches was 1. This means that I was completely overfitting my classifier because I was making so much thresholds in the tree that in the end, each training instance was becoming one final leaf. So therefore, this was obviously not a real model. It was a kind of fake. Another thing, for example, is the number of nearest neighbors in a k-nearest neighbor. So if you base your decision on the category based on just one neighbor, maybe, you are not generalizing a lot. This can be very good for very heterogeneous spaces where no clear distribution is made. So maybe this is interesting there, but it always depends on your task and your objectives, no? There is a complexity parameter in the SVM, which also specifies the complexity of the task. And in classifiers which use a distance, such as the KNN, for example, again, be careful on which distance you choose, because this completely changes the results. And usually in Weka you have different distances to test there. Or, depending on the distance, the effect of normalization can be really important. Then another thing, if you evaluate the features, not the classifier, if you want to devise features for a certain category or for annotating a certain type of songs, first use several classifiers. So you want that your features can be exploited by many classifiers, not just by one classifier. No, you want that your features provide benefits to many types of classification algorithms, not just a particular one. So you want to demonstrate this accuracy increment given your features with different classifiers. Sometimes it's a good idea to include a one-rule classifier. A one-rule classifier just selects one feature and classifies with one feature. This is not going to give you the best accuracy, but it's going to give you an idea of if it's worth considering more than one feature, for example, or not. Then, if you want to demonstrate the usefulness of your features, use several data sets also. Apart from using different classifiers, it's good that you test it on several data sets. Maybe your data set is biased. Then another good practice is to report the random baseline. So report the average accuracy of just guessing the category of that instance, but also report the standard deviations. If you just report the mean value, you do not get the correct sense of where is your random baseline, up to which point it gets. And finally, if you are comparing a feature set, include a baseline feature set. So take some features that have been used for this task or whatever and report these results also in your experiments. No? For example, here is a table from an article we published. In this case, we were comparing some new features, these SBSC features, implemented in various ways, ABC, and we were doing a general classification task in this case, where we wanted to show that these features were good for classifying genres. No? So here is just a small table, but ideally these tables should be higher. We reported the random baselines in text below in the table caption, and we considered 3 different classifiers, 2 different data sets, a baseline set of features, and we ran all these experiments. With this, we could check that, okay, this accuracy increases independently of the classifier you choose, independently of the data set you choose, so you can be more confident that your features are a little bit better than the baseline. But all these increments are not meaningful if a statistical significance is not assessed. And this is the last issue you need to care about when doing classification or annotation-based problems. Always assess statistical significance. So an increment is not meaningful at all if it's not statistically significant. And usually the packages I've mentioned before provide very easy ways. You don't need to be a statistician to understand this kind of methods. So they provide easy ways to assess that, and it's really fast to do it, and it's worth it. So basic conclusions. In category-based retrieval, you retrieve music based on automatically annotated labels from audio. So the task is to assign a label class and a probability of this label and a confidence value of these assignments to a given audio piece. In automatic annotation, there are three main steps. We have overbuild, feature extraction, feature transformation and selection, and then the classification stage. And finally, we have overbuilt some really basic issues in these tasks, but that are worth to keep in mind. And that's the end of the presentation. Thanks for the attention. And yeah, maybe there are no questions here. I don't know.